Hey again everyone. In the last video, I covered the IEEE 754 standard for floating point numbers. In this video, I'll show you how to work through converting a decimal to a float by hand. Let's get straight into it. Suppose you have this number, 1234.212. Where do you even start with converting this number? Well, in the last video, I mentioned that floats are a lot like scientific notation, but for binary numbers. You probably got an idea of how similar the bits in a float are to just a regular normalized binary number. So what should our steps look like? Well, first, we should take our decimal number and convert it to binary. We wouldn't want to normalize the decimal number first. That would make life difficult for us. Normalization will come second. All we have to do after normalizing the number is essentially rearrange the bits to look like a float. That part has a few sub-steps involved, so we'll go over those once we get there. Let's begin by converting this number into binary. To convert a decimal number with a fractional part into a binary number, we convert everything after the point separately from everything before the point. This means we can start by just converting this number, 1234. There's two popular ways that I've seen to convert a decimal integer to binary, the division method and the subtraction method. We'll do both, and you can pick which one you prefer. In the division method, we start with the number we're converting, and we repeatedly divide it by 2, keeping track of the remainder. Start with 1234. We divide it by 2, and we get 617, no remainder. Divide 617 by 2. We get 308, with a remainder of 1. Remember, since we're dividing by 2, we will only ever get remainders of 0 and 1. We continue dividing, until we get 0 remainder 1. Now all we have to do is put those bits in reverse order, from bottom to top. We get 10011010010. Next, let's look at the subtraction method. This one is good if you're working with a relatively small number, on the order of 5 digits or less, and you know your powers of 2. In this method, you keep subtracting the closest power of 2 from the number. The power of 2 must be less than the number. You cannot have a negative result. Let's work through it step by step so you can see what I mean. Start with 1234. The closest power of 2, without going over, is 1024. We subtract that from our number and get 210. The closest power of 2 to 210 is 128. Subtract that and we get 82. We keep doing this until we end up with 0. Now we know the final number contains 5 ones, one in the 1024's place, one in the 128's place, one in the 64's place, 16's place, and 2's place. Fill in the rest with zeros, and that's your final answer. Okay, so if you're in comp sci, you probably knew all that already, so let's get on with the fractional part. We have 0.212. Fortunately, this is easier than the integer part. Well, in my opinion anyway. Let's take a look. The method here is the opposite of the division method. We repeatedly multiply the number by 2 and keep track of the ones place. Start with 0.212. We multiply that by 2, and we get 0.424. We notice that the ones place is 0. Next, we multiply 0.424 by 2. We get 0.848, and notice that the ones place is still 0. Here's where it gets interesting. We multiply this by 2, and we get 1.696. The ones place is 1, so we write that down. But when we multiply again, we have to take away that 1. We do this every time we get a 1 in the ones place. Here you can see what I mean. We took away the 1 and ended up multiplying 0.696 by 2 and getting another 1 in the ones place. But this could go on for a while, possibly even forever. So how do we know when to stop? If you remember my last video, I mentioned that the fraction part of a float is 23 bits long, plus an extra hidden bit, making it technically 24 bits. That means 24 digits is our target number of digits to reach when we're converting our decimal to binary. When we converted our integer part, we got 11 bits. Subtracting 11 from 24, we see that we still need to find 13 more digits. I'll spare you the pain of watching me convert the rest of the digits. Notice that when using the multiplication method, our final bits are read from top to bottom. Now let's put the integer and fractional parts together. Here's our final number. Notice how it is exactly 24 digits long. We're done with step 1. Now on to step 2, normalizing the number. Normalizing is probably the easiest step. All you have to do is shift the dot over until all that remains on the left is a single 1 in the ones place. All that's changed here is the location of the dot. That's not entirely it though. We also have to remember to multiply by 2 to the power of x, where x is the number of times you shifted the dot to the left. Now that we have our normalized number, we can move on to step 3, building the binary float. We're almost done. The final step is to put the bits into the format of a float. Remember that a float has 3 parts, the sign, exponent, and fraction. In this case, our number is positive, so the sign bit is 0. When it comes to the exponent, remember to add the bias. Our exponent bits should be 10 plus 127, or 137. You'll have to convert that exponent to binary. I'll show you the result here. Finally, there's the fraction. Again, if you remember, the fraction is just all of the significant digits except for the leading 1. So we remove the first one and there's our fraction. Putting those together, we have our binary float. Before I close this out, I just wanted to throw in a couple things of note. First, if you're converting a decimal in scientific notation to a float, you need to get it out of scientific notation. Do the multiplication and get it looking just like a regular number with only one term. Then do your conversion. Second is to keep in mind special numbers. If you watched my last video, you should know to look out for 0 or infinity, since they have special representations as floats. And that's about it. I wanted to get to converting doubles, but it turns out making videos like this is a lot of effort. If you really want me to get into doubles, just let me know in the comments or on Discord. But just keep in mind, I probably won't be able to get around to uploading that until a few days from now. Anyways, that's it. Thanks for sticking around.